Welcome, comrades perennials, to another episode of the audio podcast, Synthetic. Artificial intelligence will not replace you, but someone using artificial intelligence definitely will. So, imagine you are looking out the window of a passenger jet, right?
Oh, yeah, like cruising at 30,000 feet.
Exactly. And you're flying directly over the mouth of this massive river, like the Mississippi or the Po in Italy. And if you look down at the coastline, the landscape just looks like absolute untamed chaos.
Right, it looks totally random.
Yeah, the river shatters into these hundreds of tangled veins of water just bleeding out into the ocean. It looks like shattered glass, or the roots of a dying tree. But the fascinating thing is, beneath all that apparent chaos, there's actually this perfectly calculated, almost terrifyingly precise mathematical architecture.
It's true. Those wild forces of nature are actually following strict, inescapable geometric rules.
Right. And today we're exploring exactly how water carves the earth. We'll start from the sprawling networks of upstream rivers, zoom all the way into the microscopic physics of a single drop of water forming a channel, and then hit this massive 2026 breakthrough.
Which is huge, by the way. It reveals exactly how coastlines defend themselves.
Exactly. And, this is just some abstract math puzzle for us to talk about. If you live anywhere near a coastline, these equations literally dictate whether the land beneath your feet will survive rising oceans over the next few decades, or if it will just, vanish.
Yeah, and unlocking what happens at the coastline actually requires us to understand the rules governing the water long before it hits the ocean.
Right, the upstream stuff.
Exactly. Mathematicians and geologists have spent decades trying to find the underlying order in the shape of river basins. And back in 1957, this American geologist named John T. Hack noticed something wild.
Hack's law, right.
Yeah, Hack's law. He found this bizarre, consistent scaling law hiding right there in the maps of river networks. Basically, you can predict the total length of a main river stream just by looking at the total area of land that drains into it.
Wait, really? Just from the land area?
Yeah. The relationship is governed by a specific mathematical exponent, which is usually between 0.57 and 0.60.
Okay, so what does that exponent actually mean in plain English?
Well, think about it this way. If river basins grew in perfect symmetrical circles, the math says the exponent would be exactly 0.5.
But nature doesn't build perfect circles.
Precisely. River basins are trapped by the landscapes around them, so they're forced to stretch out, elongating into these narrow ovals as they get bigger.
I see. So that specific exponent, the 0.57 to 0.60, proves that rivers scale up in this predictable, nonlinear way, completely regardless of the climate of the continent.
Exactly. And to visualize this massive network, scientists use a system called Horton-Strahler stream, ordering to map out the geometry.
Horton-Strahler. I've always thought of that like pruning a giant oak tree from the very tips of the branches inward toward the trunk.
That is a perfect way to picture it.
Yeah, so in a river system, those tiny little trickles of water at the very top of a mountain, those are your first-order streams, right?
Right. And when two of those first-order streams finally meet and merge together, they bump up a level. They create a slightly larger second-order stream.
And the two second orders make a third order, and so on. It just cascades down the mountain.
Merging over and over until you get those massive, deep trunk rivers dumping into the sea. It takes this chaotic web of water and forces it into a strict hierarchical grid.
Which leads right into Tokunaga's law, doesn't it?
Yeah.
And Horton's laws of stream number and length?
Yes, exactly. Those principles show that river networks have what we call structural self-similarity.
Meaning they're fractals.
Basically, yeah. The branching pattern looks mathematically identical whether you're zooming in on a tiny 10-mile creek or zooming out to see a 1,000-mile river basin.
Wow. And the math predicts exactly how many smaller tributaries will feed into a larger stream at any given point, right?
It does. And this creates something called uniform drainage density. Across any specific landscape, the average distance between individual river channels stays remarkably constant.
It's like the land absorbs channels like a sponge to a very specific saturation point.
Exactly. Once it hits that point, any drop of rain that falls only ever has to travel a characteristic, predictable distance over the ground before it tumbles into a channel.
Okay, but let me push back on this a little bit. Because a completely rigid mathematical grid governing a wild landscape, it intuitively feels like humans just forcing clean equations onto a messy reality.
It sounds like we're just seeing patterns in the noise, right?
Yeah. Does nature actually care about these geometric ratios? The dirt and the rocks don't care about exponents.
They don't. But the mathematics aren't just some artificial overlay. They are the literal reflection of a landscape reaching absolute physical exhaustion.
What do you mean by physical exhaustion?
Well, the ratios emerge precisely because the water is trapped by the physical limits of its environment. The system is constrained by how easily the local soil crumbles, the sheer volume of rainfall, the steepness of the terrain.
Ah, okay. So a landscape will only carve new channels until it physically runs out of space or gravitational energy.
Precisely. The math perfectly mirrors that state of maximum channelization. It's the inevitable result of water taking the most efficient possible path through a medium that constantly resists it.
So if that macro level view shows this fractal network driven by physical limits, I have a micro level question. How does that very first tiny scratch in the dirt actually form?
That is a great question. Before it joins the big mathematical hierarchy, a single channel has to be born on a seemingly flat hillside.
Right, and mathematicians use these highly complex hydrodynamic models for this, don't they?
Yeah, like the models from Fowler, Koptiva, and Oakley. Instead of abstract geometry, they use things like the St. Venant equations.
The St. Venant equations, what do those calculate?
They calculate the sheer physical momentum of the water rushing downhill, and they balance that force against the stubborn friction of the soil using the Exner equation for hill slope erosion.
Okay, so it's momentum versus friction. But there's a crucial detail here, the bedload layer thickness.
Yes, this is vital. The bottom of a fast-moving stream isn't some clean, flat surface.
Right, it's a chaotic, tumbling conveyor belt of loose sand, gravel, and submerged rocks just rolling along the bottom.
Exactly. And earlier mathematical models completely failed because they treated that moving layer of rubble as if it had zero physical thickness.
Which would mean what? The math just assumes water slices right through solid rock.
Exactly, which it doesn't. By forcing the models to account for the physical space that tumbling layer occupies, scientists draw a hard line between two distinct types of erosion.
Let me guess. Transport limited and detachment limited.
You got it. The Meyer, Peter, and Mueller formula really highlights this. Transport-limited erosion is when the water is just carrying away loose, available dirt.
And detachment limited is when the water actually has to chisel and tear away solid bedrock.
Right. And that tumbling layer of rocks actually acts as a protective shield over the bedrock. The math has to reflect that water struggles immensely to carve solid stone without a massive amount of kinetic energy.
Okay, but what's the actual trigger? What starts that first cut?
It relies on a highly specific geometric anomaly on the hillside. The ground has to curve slightly upwards.
Like the inside of a bowl, a concave slope.
Exactly. When a broad, uniform sheet of water flows over a flat slope, it stays stable. But the second it hits a concave slope, the uniform flow breaks down completely.
Okay, picture this. Imagine a chaotic crowd of 50,000 people trying to leave a massive stadium at the end of a game. At first, everyone pushes forward as one giant, uniform mass.
But as the pressure builds, people naturally find the paths of least resistance.
Exactly. They funnel toward the exit ramps. The uniform mass rapidly coalesces into these dense, highly concentrated streams of movement. Water on a concave slope acts identically, right?
That is exactly how it works. The physical instability forces the broad sheet of water to funnel together, which instantly concentrates its destructive energy into tiny, distinct channels in the dirt.
And the moment that funneling starts, this unstoppable physical feedback loop kicks in.
Oh, yeah. Because as water rushes into that new depression, the water gets deeper. And deeper water carries way more momentum.
It flows significantly faster than shallow water.
Right. And that acceleration drastically increases the frictional drag the water exerts against the sediment on the bottom. In fluid dynamics, this is called the shield stress.
So as the shield stress skyrockets, the water rips away more soil, digging the channel deeper, which pulls in even more water, which makes it even faster.
It's an explosive cycle of erosion. A microscopic dip in the soil rapidly accelerates into a permanent geographical scar.
Okay, so upstream, the rules say water has to gather and consolidate its power, carving deep into the earth. But eventually, this massive, highly organized system slams into the coastline.
And it shatters into a delta.
Right. And this brings us to that massive 2026 study in the journal Science, led by Tian Weidong, Hongguo Ma, and Alejandro Tejedor. They wanted to know if those rigid mathematical laws survive the transition into the ocean.
Yeah, they analyzed satellite imagery of 29 major global deltas, totally different environments, from the Po River in Italy to the Wax Lake Delta in Louisiana, even the freezing Selenga River in Siberia.
And what did they find?
The core discovery was the existence of an apparent Hacks law, but operating in reverse within river deltas.
In reverse, how does that work?
Well, upstream, the original Hacks law says the length of a single gathering river scales with the massive area of land draining into it. Deltas are a mirrored system. They are distributary networks spreading out from a single point.
But despite that structural reversal, they found a nearly identical mathematical scaling relationship, right?
Yes. In a delta, the length of the distributary channels scales with incredible predictability against what they call the nourishment area.
And the nourishment area is basically the exact footprint of new land that the spreading channels are building and maintaining with sediment.
Exactly. And the 2026 study also revealed two entirely different behavioral patterns within this scaling law.
Right. Uniform networks and composite networks.
Yep. Uniform networks strictly obey this apparent Hacks law from the moment the river begins to split all the way to the ocean.
But composite networks are wild. They begin in this state of unpredictable chaos. Near the apex, the channels spread outward violently, almost like ink dropping into water or a fireworks explosion.
But then, as those channels lose their initial explosive energy and get closer to the sea, they suddenly fall back into the mathematical rhythm. They organize into these quasi-linear, predictable streaks.
But wait, this presents a massive physical contradiction. Upstream rivers exist to gather water from a vast area into a single point. Deltas exist to disperse water from a single point out into the ocean, fighting waves and tides.
Right, they have completely opposite goals.
So how can the exact same mathematical equation govern both processes?
It all comes down to the foundational efficiency of natural systems. Whether a branching network is pulling water out of a continent or pushing mud into a sea, the systemic mandate is absolute efficiency.
So the upstream network expends the least amount of energy to drain the landscape, and the downstream network expends the least energy to distribute sediment.
Exactly. It creates a mirrored geometric reality. The geometry of a branching network is just fundamentally the most efficient way to move volume across a surface area. The physical direction of the flow is entirely secondary.
Wow. And to really understand why a delta structures itself this way, we have to look at the thermodynamic pressures pushing against it, like Alejandro Teixedore's 2017 PNAS study.
Ah, yes. The study on entropy and optimality in river deltas, they introduced a metric called the non-local entropy rate, or NER.
Right, the NER, which basically shows that deltas don't just dump their water and sediment through one massive central pipe.
No, they naturally self-organize to maximize the diversity of their delivery pathways. The delta actively seeks out a state of high entropy.
It's constantly splitting and fracturing its channels to make sure sediment is spread across the widest possible variety of routes to the shoreline. But why?
Resilience. A high non-local entropy rate provides the delta with an indispensable survival mechanism. By intentionally diversifying those pathways, local damage doesn't destroy the whole system.
So if a massive storm or a rising tide chokes off one specific channel with debris, the network just seamlessly absorbs the displaced water elsewhere.
Exactly. But this defense mechanism does have a breaking point. When an environmental shock drastically exceeds the delta's capacity to absorb the energy, it triggers an avulsion cycle.
An avulsion, that's a sudden, violently catastrophic reorganization of the landscape. Right?
Yeah. The river simply abandons its primary choked-off channel, bursts right through its own banks, and aggressively carves an entirely new path to the ocean.
It's a drastic, destructive reset button. It instantly restores the delta's optimal entropy. You know, this whole thing, a delta constantly shifting and managing its own diverse pathways, it really echoes the behavior of other complex natural systems, like ant colonies.
Ant colonies, how so?
Well, biologists observe ant colonies pulsing in these synchronized bursts of activity. The whole colony undergoes a massive phase transition, shifting its behavior without any central queen or leader directing the individual ants.
Ah, it regulates itself purely through localized interactions.
Exactly. And a delta acts essentially the same way. It's this massive, leaderless physical entity, dynamically pulsating and rearranging its geometry to find the optimal state.
That is remarkably accurate. The delta is a highly dynamic, self-regulating entity that actively manages time. It decouples the really fast, chaotic timescale of daily hydrology, like shifting tides and storms, from the exceptionally slow, century-long timescale of land building.
And those violent avulsion cycles are the vital pulses of the system.
Right. Periodic resets that clear out geometric inefficiencies, making sure the massive landmass survives the daily assaults from the ocean.
Which brings us to the urgent practical reality here. Because this mathematical reality isn't just theory, it lands squarely on the crisis facing modern coastal infrastructure.
Yes. Densely populated coastal cities from New Orleans to Venice are in extreme vulnerability right now. Sea levels are rising and the ground is sinking.
The survival of millions of people depends on how we manage the geometry of the coast. And that 2026 discovery of the apparent Hacks law gives engineers a precise, quantitative rule of thumb.
It does. By looking at whether a delta has uniform or composite growth, engineers can actually calculate the physical limits of a disappearing coastline.
So they can predict exactly where a delta is mathematically capable of building new land and where it has hit its absolute geographic limit.
Precisely. If the math dictates that a specific region is completely saturated and can't expand further, pumping millions of tons of dredged sediment into it is just a futile waste of resources.
It ensures that limited coastal restoration funds are used strictly in zones where land expansion is geometrically viable. But wait, this brings up a huge conflict. If a delta mathematically requires periodic, catastrophic avulsion cycles to survive, aren't our modern flood controls completely backwards?
Absolutely.
We build these massive concrete levees to lock the river into one permanent, unmoving channel to protect cities. But the equations say the river must eventually pulse and change course.
Yeah, locking the river in a rigid concrete cage is basically a direct declaration of war against the physical laws of fluid dynamics.
So how do we survive then?
By abandoning the war against physics, modern engineering is shifting away from rigid confinement and moving toward mimicking the mathematics of natural land building.
So instead of forcing a river to die inside a static channel, we use Hacks law to strategically initiate controlled avulsions.
Exactly. By carefully fracturing the levees at mathematically calculated points, we can safely redirect the water and sediment. It actively facilitates the delta's inherent drive to maximize its non-local entropy rate.
Wow. Aligning human infrastructure with the universal scaling laws allows the river to build sustainable, defensive landmasses naturally.
Protecting populations without suppressing the unstoppable energy of the water.
And the implications of these geometric scaling rules, Hacks law, Horton-Strahler ordering, maximum entropy, they go way beyond Earth.
Oh, definitely.
If these equations represent a universal physical necessity for any fluid moving across a substrate, we could use them to decode other worlds, like the ancient fossilized river networks carved into Mars.
Right. By running the equations backward through the alien geometry, we could calculate the precise volume and velocity of the water that flowed there billions of years ago.
And looking even further, this could be the mathematical blueprint for algorithmic terraforming. If humanity ever tries to engineer synthetic coastlines and river deltas entirely from scratch on new worlds, the designs will be dictated by these exact same equations.
Forcing the chaotic forces of alien oceans to obey the hidden, unbreakable architecture of water.
Exactly.
Subscribe to the podcast series Nuclear Locomotive, Neural Sawdust, and Synthetic. Namaste, thank you, and good luck.